All right, let's get right into it. Welcome to today's explainer. Today, we are unpacking Class 9 Mathematics, specifically Chapter 1, Orienting Yourself, the Use of Coordinates. We're going to take what looks like a bunch of abstract mathematical numbers and grids and completely transform them into your own personal GPS system for the Cartesian plane. If you've ever felt kind of lost just looking at a graph, don't worry, you absolutely won't be by the end of this session.
You know, there's a great quote from our source notes that really hits the nail on the head. Just like a GPS helps us find locations, coordinates help us find exact positions on a plane. We really aren't just plotting random dots on paper just for the fun of it. We're actually learning the foundational language of maps, of navigation, and honestly, even video game design. Mastering this chapter matters in the real world because this is exactly how you pinpoint where you are and figure out where you need to go.
So, here's our game plan for today. We'll start with why coordinates matter, move on to building the Cartesian plane, learn to navigate the 4 quadrants, tackle distance and midpoint formulas, and finally, we'll put it all to the test.
All right, first up, building the Cartesian plane and laying the groundwork.
Before we can start finding our way around, we really need to clearly define the map we're actually going to be using. So, what exactly is the Cartesian plane? Well, as our revision notes define it, it's a flat surface formed by 2 perpendicular lines used to locate points. I want you to think of it exactly like a giant city grid. You have your x-axis, which is entirely horizontal. Let's go ahead and call it X Avenue. And cutting right across it vertically is your y-axis, or Y Boulevard. Every single movement, shape, and calculation we do happens right on this flat, intersecting grid.
And the absolute most crucial part of this grid? The origin. This is the exact intersection where X Avenue and Y Boulevard meet. It's represented by the coordinates 0, 0. Every single journey on the Cartesian plane starts right here at the origin. It's basically the ultimate starting block for our mathematical GPS. Before you go left, right, up or down, you always start at 0, 0.
Now, let's break down some of that tricky math jargon you're definitely going to see in your test papers. First up is the word abscissa. Honestly, that's just a fancy mathematical term for the x-coordinate. What it actually represents is your distance from the y-axis. When you see a coordinate pair, this number tells you exactly how far left or right you need to walk along X Avenue.
And right alongside it, just to make sure you don't get the two mixed up, we have the ordinate. This is the term for your y-coordinate, which represents your distance from the x-axis. So it tells you how far up or down you're traveling on Y Boulevard. To keep them totally straight in your head, just remember, abscissa is your horizontal address and ordinate is your vertical address.
Moving right along to Section 2, navigating the 4 quadrants and reading the map.
So those 2 axes we just built, they intersect and slice our map into 4 distinct zones, which we call quadrants. And each of these 4 quadrants has a very strict sign convention. Quadrant I is positive, positive. Quadrant 2 is negative, positive. Quadrant 3 is negative, negative. And quadrant 4 is positive, negative. And this brings up a fantastic trick from our revision notes. Always start from the top right and move in an anti-clockwise direction. Seriously, if you just draw a circle to the left, starting from quadrant I, you're going to label your quadrants perfectly every single time.
Let's actually visualize this theory by looking at our map. See how the positive and negative signs accurately drop points A, B, C, and D perfectly into their respective quadrants? Point A is at 3, 2. Both numbers are positive, so it lives right there in quadrant I. Point B is at negative 2, 1, a negative horizontal and a positive vertical, placing it perfectly into quadrant 2. Point C at negative 3, negative 2 lands squarely in quadrant 3 because both are negative. And finally, point D at 2, negative 3 sits in quadrant 4. It's really all about reading those positive and negative signs as precise directional instructions.
Okay, on to Section 3, distance and midpoint formulas. These are our advanced navigation tools.
Now that we know how to pinpoint any spot on the map, we need some advanced GPS tools to measure entire trips or, say, find halfway points. Imagine you're mapping out a route and you need to find the exact center of a line segment. For that, you need the midpoint formula. The revision notes break this down into 3 super straightforward steps. Step 1, add the x-coordinates of your 2 endpoints together and divide by 2. Step 2, add the y-coordinates and divide by 2. Step 3, write your final answer as a brand new coordinate pair, x, y. You're basically just calculating the average of your horizontal distances and the average of your vertical distances to find the exact middle. Easy, right?
But what about finding the total length of a trip? This is where comparing the theoretical math to the practical math is absolutely crucial. Check out the theoretical distance formula from the notes. It's that big square root equation you see. It looks like a whole lot of heavy math, doesn't it? But look at the practical geometric application right next to it. When you plot points on the grid, like finding the distance from 5, 0 to 0, -6, you are really just drawing a geometric right triangle. This brilliantly shows that the distance formula is literally just the Pythagorean theorem applied to our Cartesian grid. You're just calculating the hypotenuse. Mind blown, right?
Finally, Section 4, putting it to the test in our flight simulator.
All right, we've built the map, mastered the signs, and packed our advanced tools. Let's dive right into the Ganita Manjari test paper from our sources to see if you can navigate on your own. Here's a rapid-fire multiple-choice question for you. The point 0, -5 lies on which axis? Is it A, the x-axis, B, the y-axis, C, the origin, or D, the first quadrant? Take a second and really think about what happens when your x-coordinate is 0.
If you guessed B, the y-axis, you are totally correct. This perfectly reinforces that rule about points lying flat on the axis lines. A point sitting on the y-axis is always going to have an x-coordinate of 0 because you simply haven't moved left or right at all. You've just moved straight down 5 units.
Let's throw one more quick multiple-choice question your way, just to make sure you've really got a handle on reading these coordinate pairs. The x-coordinate of the point 7, -2 is A, -2, B, 2, C, 7, or D, -7.
And the answer is C, 7. The x-coordinate, or the abscissa, is always the very first number listed in the pair. Just a quick, enthusiastic reminder, your horizontal address always comes before the vertical address. No exceptions.
We've covered some fantastic ground today, literally turning a blank grid into a fully functional navigational tool. But before we wrap up this explainer, I want to leave you with a final, provocative challenge right out of the long answer section of the test paper. Looking at points A at 4, 6, B at -5, 3, C at -3, -4, and D at 6, -2, which point is farthest from the x-axis? Think very carefully about what distance from the x-axis actually means in terms of your y-coordinate. Does a negative sign mean it's closer or just in a different direction? I'm going to let you ponder that puzzle. Keep mapping, keep exploring.